Okay, Algebra 2, as we move into section 3.1 with the beginning of chapter 3 here, we're kind of shifting gears a little bit. We're still going to be talking about linear functions here, but we're getting into something called a system of equations, and this is new for us here, so we better start with a definition of terms before we go too far. A system of equations involves two or more equations. So first thing we want to understand, we're talking about multiple equations here, and in most cases, those equations are going to involve two or more variables. So we just got done in chapter 2 dealing with two variable equations and some inequalities in there as well. Now we start dealing with two of them at the same time. And we're going to start, as the title of this section suggests, we're going to start solving systems of linear equations. So in order to understand what it is that we're looking for, this definition right here becomes important. A solution to a system of equations has to satisfy each equation in the system. Meaning, should be a period right there, sorry, meaning that any solution we come up with needs to be a solution not just to one of the equations in your system, but to all of them. So that's an important concept. Now, we could say more about things right now, but it's really not worth it. Let's just dive into an example, and we'll talk about what it is that we're trying to accomplish here. So the directions in number 2 are pretty straightforward. Solve each system. So let's go back to this definition that we wrote down right here. To solve a system, we're looking for an ordered pair, an x value and a y value, that satisfies each of the two equations in this system here. So our first one in blue is y equals 1/2 x plus 4, and a second two-variable equation is given to us in red. Y is equal to negative 2x minus 1. Now, as I'm hoping you guys remember from Algebra 1, what you're dealing with right here is a two-variable equation, and the number of solutions to a two-variable equation is infinite. Now, just to prove my point, I could come up with a few right here. For example, if I were to let x be 8, I think I could figure out what y is. 1/2 times an 8 right here would be 4. 4 plus another 4 would be 8. So 8, 8, the ordered pair, is a solution to this blue equation. Now, if, by dumb luck, that were also a solution to this red equation right down here, we would have found our solution. But let's check it real quick. If I put an 8 in here, let's take a look. 8 for x. Negative 2 times 8 is negative 16. Negative 16 minus 1 is negative 17. Okay, so I didn't get lucky here, guys. The solution here, when x is 8, is 8, 8. And if this one in red happened to be 8, 8 as well, we would have found it, but it didn't work out that way. So none of that is surprising. You don't just randomly guess a number and hope that you're going to get the right solution. What we're going to do instead is use a method called graphing of finding our solution to our system. And we're going to graph each of these two linear equations just like we were doing in chapter 4. So for the first one, y is equal to 1/2 x plus 4. We have a y-intercept of 4 and a slope of 1/2. So up 1 and 2 to the right. And I'll keep doing that. It's even more important here than it used to be. Up 1, right 2. I'll guess here up 1, right 2 again. And I'm going to go the other direction as well. Down 1, left 2. Down 1, left 2. Down 1, left 2. And that's probably pretty good. Now, what's important for us to understand here, guys, is that every single point that we just came up with is a solution to this blue equation. So just if I were to pick one at random, like, I don't know, this point right here, you don't have to write this down in your notes, guys, but that is the ordered pair 4, 6, if I'm not mistaken. Let's see if that works. Our y value there is 6, and that equals 1/2 times an x value of 4 plus 4. Well, half of 4 is 2. 2 plus 4 is 6. So we end up with 6 equals 6. That's a true statement. So 4, 6 is one solution to that blue equation. But unfortunately, there's too many of them to list. All of those dots that we have on the graph right now are solutions to the blue equation. So I can't ask you to list all of them. That is why we graph a linear function. So let's make sure we understand something from geometry last year. How many points are on that blue line? well, the number of points on any line is infinite. And then, going along with that, how many solutions are there to a two-variable equation? The same number, infinitely many. Every point on the line is a solution to this equation. And spin that around, every solution to this equation would fall on this line when we plotted it. So now let's shift gears. Now let's take a look at the second equation. Y is equal to negative 2x minus 1. This is again a two-variable equation, which again has an infinite number of solutions. So I can't ask you to list all of them. Let's graph them then. Negative 2x minus 1 has a y-intercept of negative 1. And a slope of negative 2. So I would go down 2 and right 1, down 2 and right 1. And there's no point in going any further in that direction because you'll notice we're moving farther away from the blue line. But if I shift gears and go up to left 1 and one more time, up to left 1, right here something interesting happened. I just found a red point, a solution to the second equation that was also a solution to the first equation. So I guess I could go a little further if I wanted to, and I'll go ahead now and draw this line connecting all of those red dots. Now once again, there are an infinite number of solutions to this equation here and an infinite number of points located on that line. But what we are interested in here, everybody, is the one and only point here that is on both of those lines. And it's this ordered pair right here, where those two lines cross, that is the one and only solution to this system of linear equations. That ordered pair right there, which looks like negative 2 and positive 3 for the y-coordinate, is the only ordered pair that's on both the blue line and the red line, which means it's the only ordered pair that's a solution to the first equation and to the second equation. So this is our answer. Now, let's double check it. Let's make sure that the ordered pair negative 2, 3 works in each equation. So in the blue equation up on top, my y value is 3. And that equals 1/2 times an x value now of negative 2 plus 4. Well, 1/2 of negative 2 is negative 1, and when we add negative 1 plus 4, we get 3 on the right-hand side. And 3 equals 3 obviously is a true statement. So this ordered pair, negative 2, 3, satisfies the first equation. But to be a solution, it also has to satisfy the second. So let's check it down here. Y is 3. And that should equal negative 2 times an x value of negative 2 again, minus 1. So 3 is equal to negative 2 times negative 2 is positive 4, and 4 minus 1 is 3. Once again, we get a true statement, and check, this solution satisfies the second equation as well. So because this ordered pair works in both the first equation and the second equation, this is our solution to this system of equations. So that should hopefully give you a sense of what it is that we're trying to accomplish here. We're trying to find any ordered pairs that satisfy both of the statements, or in some cases it could actually be 3 or 4, but it's almost always 2. This is the only ordered pair that does that. Make sure when you get done with this problem on your homework, everybody, that you actually list the ordered pair as your solution. You can't just give me the graph and then leave it up to me to figure out what ordered pair that is. Okay, so basically, guys, that's what section 3.2 is all about. Let's do a couple of different examples here, and a couple curveballs get thrown at you here, and I didn't wait long to give you one of these. So let's check this one out. First, y is equal to 2/3 x plus 1. Y-intercept of 1 and a slope of 2/3 means up 2, right 3. Up 2, right 3. I could also have gone down 2, left 3, down 2, left 3, and there you go. So we will go ahead and draw the line. That's a pretty good line, passing through all of those points. There are an infinite number of solutions to this equation and an infinite number of points on the blue line that we just drew. Now let's draw our second one. Y is equal to 2/3 x minus 4. And if you think really hard for just a second about what this red line is going to look like before we graph it, you might start to see why this is kind of an interesting example. Our y-intercept now is negative 4. So there you go. We start with a dot right there. And our slope for the red line is up 2, right 3. Up 2, right 3, up 2, right 3. And of course, I could go down 2, left 3 as well. And what you may have noticed now is that when we go and we draw the line connecting all of those red points, we were looking, let's go back to the previous example, we were looking for the spot where those two lines intersect. Where does that happen here? It doesn't. And the reason that these two lines don't intersect, I'm sure you've noticed by now, is that these two lines are parallel. So we're going to go ahead and just make a note of that. Our two lines right here are parallel. And since we're looking for a point of intersection that satisfies both of the two equations, what we can realize here is, wait a minute, these two lines had the same slope and different y-intercepts. That is what makes them parallel. And where do two parallel lines cross? They never do. And so the answer to this problem, everybody, is no solution. Okay, and that is what we box up. So let's be loud and clear about what it is that we've accomplished. Equation number 1 here in blue has an infinite number of solutions. Equation number 2 also has an infinite number of solutions, but there is no ordered pair that exists that works in both statement 1 and statement 2 at the same time. We were able to find one of those in the previous example here, this ordered pair of -2, 3, but there is no such ordered pair here because your lines are parallel. Okay, couple more things thrown at you right here. Okay, this one, now the plot thickens a little bit here, guys. The first equation is just the way we like it. Y is equal to 2x minus 4 is in slope-intercept form. So our y-intercept, wow, I think for the third time today, good job, Fontana. Our y-intercept is -4 yet again, and our slope is 2. So up 2, right 1, up 2, right 1, up 2, right 1. Okay, I get it. And we will go ahead and draw the line now connecting all those collinear points. There are an infinite number of solutions to that equation and an infinite number of points on this line. Unfortunately, I'm going to make you guys work for this one. The second equation in red is given to you in standard form. And standard form we don't do a whole lot with other than trying to solve it for y. So what we're going to do here first is subtract a 6x from both sides of the equation. Those terms will cancel, and we're going to get -3y is equal to, and most of us I think would prefer to have that written in this order, -6x plus 12. Now, to get y by itself, we're going to divide out that -3, and of course that needs to get divided on each term in the equation. -3's cancel. We're going to get y is equal to, and now something interesting is going to happen. -6 divided by -3 is +2. So y is equal to 2x. And then for the constant at the end, we have a +12 divided by a -3. That is -4. So the second equation, which was in standard form, has now been rewritten in slope-intercept form. So let's graph it. Our y-intercept, is -4. That sounds familiar. And our slope is 2. Up 2, right 1, up 2, right 1, up 2, right 1. And by this point, you probably realize that when I go ahead and draw in the second line, it is the exact same line as the first one. And you probably might have noticed that a minute ago. Y is equal to 2x minus 4. Y is equal to 2x minus 4. We were being asked to graph the same line twice. So let's go back and see. We're not done with this problem yet, guys. Let's go back and look at what we learned from example A. These two lines crossed once right here, and that meant that there was one solution to this particular system, and that was the ordered pair -2, 3. In the second example we did, the lines were parallel. They never crossed, and that meant that there was no solution. Now in this one here, again, what we are looking for are points of intersection between your blue line and your red line. Well, guess what? There's a point of intersection right here, and one right here, and one here, and here, and here. But not just those 5. There's one here, and here, and here, and every single every spot there's a point on one line, that would be on the other as well. So what we have here, guys, is the same line being drawn twice. What we say in a case like that is that we have, I got to spell it right, infinitely many solutions, meaning that the number of ordered pairs that satisfy both equations simultaneously is infinite. Now, lucky for you guys, I will let you abbreviate that as IMS, but we just need to understand what that means. Infinitely many solutions. Certainly too many to list, so we'll just go ahead and we'll write that out there for that one. Okay? All right. The next two things we're actually going to skip. Solving a system using a table is a really bad idea. You end up kind of going an X and then a Y1 and then a Y2, and you're making tables here, and this is just hunting in the dark. You're randomly picking an X value here, like 0, then you're putting it into the first equation. Let's see what happens. -3 times 0 is 0, plus 20 is 20. Then you'd put a 0 in here, and I think, let's see, I think for that one right there, you ended up with, if X is 0, you ended up with -20. Not the same Y value, so 0 is not your solution. And you would just keep doing this until you eventually found a solution. It's not a very scientific method, so we're not really going to bother solving these things by tables. So I don't think we need to worry about this one then either. But this is just kind of a nice visual here that summarizes what we just discussed earlier. Our first example was this one right here, where we had two lines that were intersecting. When the two lines cross, that's when you have one solution. We're not really going to worry about these words here, guys. That's a consistent and independent system. We're not too worried about that. The second thing they have drawn, I took this graphic out of your textbook here, coinciding lines. That was the example we did right here. That just means you're dealing with the same line twice. That's when we would say you have infinitely many solutions. And again, we don't need to worry really about it being consistent or dependent. And then this third example right here is what we did on our second example. When the two lines are parallel, they never cross, that's when you would say there is no solution. Let's not worry about inconsistent. So this might not be a bad graphic to put in your notes here, everybody, but I think you had it already from those first three examples that we did. All right, everybody, that's 3.1. Now, once we move on into the next section, we're going to start to see why graphing is not always the best method in certain cases. And we'll learn something new at that point that'll get us through some of the tougher examples. But for now, 3.1, it'll work. You can graph in order to find the solution to a system of equations. Good luck, everybody.